Welcome to the second part of our lecture on scheduling in packet switches. So if you remember last time we stopped with this example of a suboptimal scheduling policy and comparing it with max wait. So we're considering a 2x2 virtual output queued switch. The arrival processes into VOQIJ for each ij are Bernoulli processes with means lambda ij. So this means that at every time slot, there's an arrival into Qij with probability lambda ij and no arrival with probability 1 minus lambda ij. Okay, so the arrival processes are independent across queues and time slots as a standard throughout this chapter. And here's the scheduling policy that we're considering. It gives priority to edges 1, 2, and 2, 1. So when we consider this switch, let's see. This is edge 1, 1, 1, 2, 2, 1, and 2, 2. And we have these corresponding queues. Let's label them Q11 at time t, Q12, Q21 of t, and Q22 of t. Now, the crosslinks are scheduled if they have any packets. This means that the links 1, 2 and 2, 1 have priority, and the links 1, 1 and 1, 2 will only be scheduled when, in this situation where there are packets in Q11 or Q22 and Q12 and Q21 are empty. Okay, so let's compute the set of lambda 1, 1, lambda 2, 2 that can be supported under this priority scheduling policy. Well, clearly, 1, 1 and 2, 2 will only receive service when there is no arrival into Q12 or Q21. Notice that Q12 of t and Q21 of t will always be 0 in this policy if we start at an initial state of 0, because whenever they arrive packets, they get service. As you know, the switch transfers 1 packet per time unit. So then these direct links will receive service only when the other queues are and when there's no arrival. So basically what I meant here was that they will be 0 just prior to service. At the end of every time slot, they are 0. If during the time slot there is an arrival, of course, the arrival comes in and then immediately it gets served. Okay, so, then the probability that Q11 gets service is the probability that Q12 and Q21 have no arrivals. And that is the product of 1 minus lambda 1, 2, 1 minus lambda 2, 1. Okay, so this means that lambda 1, 1 should be less than or equal to 1 minus lambda 1, 2 times 1 minus lambda 2, 1, because clearly it cannot support arrival rate faster than the service rate. Okay, so because of this, the same thing is true for, of course, let me right here. This, by total symmetry, the same thing is true for lambda 2, 2 as well. So lambda 1, 1 and lambda 2, 2 are both upper bounded by this. So for example, suppose lambda 1, 2 is 0.5 and lambda 2, 1 is 0.5. Then we have lambda II being less than or equal to 0.25 for I1 and 2. So if we plot lambda 1, 1 and lambda 2, 2 for this example, they will be within the square region. Okay, how about max weight? How about if we did max weight in the same situation with lambda 1, 2 and lambda 2, 1 being equal to 0.5? Clearly the constraint is lambda 1, 1 is less than or equal to 1 minus lambda 1, 2, and lambda 1, 1 similarly is less than or equal to 1 minus lambda 2, 1. Hence, this can be summarized as lambda 1, 1 being less than or equal to the minimum of 1 minus lambda 1, 2, 1 minus lambda 2, 1. In other words, lambda 1, 1 is less than or equal to 1 minus the maximum of lambda 1, 2, lambda 2, 1. The same thing is true for lambda 2, 2. So basically, let's say this is true for lambda I1 and 2. So what kind of region, capacity region, does it give us for lambda 1, 1 and lambda 2, 2? In the case where lambda 2, 1 and lambda 1, 2 are 0.5, well, this region. Clearly, this region is bigger than the other capacity region, which is here. So this small square is achieved by the suboptimal policy, and the larger region is achieved by max weight. This also is the largest possible region achievable if lambda 1 and lambda 2, 1 and 1, 2 are at this value. How do we know this is the maximum achievable? Well, because we will be able to prove that max weight is throughput optimal, so it achieves the capacity region entirely. But in order to be able to do that, we're going to need some, in order to do that proof, we need some definitions. So let's go ahead and define a doubly stochastic matrix. An n by n matrix is a doubly stochastic matrix if it has entries that are probabilities, meaning the numbers that are between 0 and 1. The entries and each row and each column sum to 1. Okay, so for example, 0.25, 0.75, 0.75, 0.25 would be a doubly stochastic matrix. A doubly substochastic matrix, on the other hand, is one where all the, again, the entries are between 0 and 1, but the column sums and row sums are less than or equal to or less than 1. So basically, it is going to be dominated by, for example, if we decrease all of these numbers, we obtain a doubly substochastic matrix. Okay, how about the permutation matrix? An n by n matrix is a permutation matrix if it is a matrix of zeros and ones such that each row and each column adds to 1, meaning in each row we have exactly 1, 1, and in each column we have exactly 1, 1. And why is it called a permutation matrix? Because if you take any matrix A and multiply it with the permutation matrix, the effect will be shuffling the rows and columns of, meaning permuting the entries of A. Okay, so there's a nice theorem that we're going to use. It's the Birkhoff-von Neumann theorem. Okay, an n by n matrix lambda is doubly stochastic if and only if it is a convex combination of permutation matrices. Meaning, there exists a vector beta that sums to 1, okay, and lambda is a convex combination of the matrices U superscript H, where the U superscript H's are permutation matrices. Now, how is this important? It will come up in the proof of throughput optimality of max weight. Okay, so here's the theorem, and essentially this is due to Tassoulias and Ephremides in their seminal paper from the late 80s, early 90s. Max weight scheduling can support any arrival rate matrix lambda which is within the capacity region. So within the capacity region means if you increase it a little bit, infinitesimally small, by an infinitesimally small value, you're still within the capacity region. So it is strictly, lambda is strictly within the capacity region. So how do we show this result? Well, we'll use the Foster-Lyapunov criterion for the stability of Markov chains. This is a usual technique that we use in this course. We define the Lyapunov function v of q. Q of t here is the vector of all q sizes. And the Lyapunov function is defined as the sum of squares of the q states. Okay, so let's take a look at the change in the value of the Lyapunov function in one time unit from t to t plus 1. Okay, now clearly the q state at t plus 1 is given by the, this is the vector, remember? So we need the sum of the entries. The ijth entry, basically qij t plus 1, is given by qij of t plus the new arrivals during time slot t minus, depending on the switch scheduling that we chose, the departures. Okay, mij of t, of course, is a matching that we use in time slot t. Okay, but of course we cannot let this q state go negative, so we take the positive part of it. Basically, if it is negative, we set it to 0. Okay, so that's that, and we have the square of these terms, and then we have the square of qij's. All right, now here we can convert this to an upper bound simply by getting rid of this positive part here, which can only increase the square. And then we simply expand this square, let's see, and subtract qij t squared, and with some algebraic manipulation you can show it's equal to this. And then we regroup the terms here. All right. Now let's see how we can proceed. Now, of course, for the argument for the Foster-Lyapunov criterion, Foster-Lyapunov test, we sometimes call it, we already know that this is an irreducible Markov chain. The q size is an irreducible Markov chain. We just have to show that it is positive recurrent. And the Foster-Lyapunov test is a test that shows us that q of t is positive recurrent. But in order for that test to work, what do we need? We need the expected difference, the expected value of this difference, which we call the drift, to be negative when the state goes out of a certain bounded region. Okay, so now let's look at the drift. The drift is defined as the expected value of the change in the Lyapunov function conditioned on the state at time t. Okay, so condition that that the q size at time t is equal to q, what is the expected change in the Lyapunov function from time t to t plus 1? All right, so up here we had already, let's see. First of all, let's take a look at this. We can always upper bound this function by ignoring the negative 2aij of t mij t term, and we can get this upper bound. Now, for the first term, all right, we clearly aij of t's are Bernoulli. Okay, Bernoulli. So the expectation of aij squared is nothing but lambda ij. Because of that, we get this. Similarly, summation mij squared is nothing but summation of mij again, because this is a matching. So basically, each entry is less than or equal to 1, so the sum is less than or equal to n. So we get this. Now this is only part of the drift. The whole drift is going to be the expected value of the conditional expectation of this thing is the drift. Okay, and that term we manipulated above will come inside of this as we work with this. Okay, so we already did this manipulation and came to this point, so we are considering the expectation of this whole term conditioned on q of t being equal to q. All right, so inside that we have this, which we already upper bounded, and it's here. And we also need to now work with this term. But the expectation of this term, in the expectation of that term, we get the expectation of aij being lambda ij. And here we have the conditional expectation of mij. All right, so we're almost there. Now, we are given that 1 plus epsilon times lambda is less than or equal to, it is within the capacity region. This means element by element, the entries of the matrix lambda satisfy the constraints of the capacity region. This means, let's see, this means that 1 plus epsilon lambda ij is less than or equal to 1 for all ij. All right, so let's use this here so first of all, let's work on 1 plus epsilon lambda ij. We know that this is less than or equal to 1, and so basically when you well, rather than 1 here, we could use the corresponding entry of the capacity region, which is defined as a matrix. But that could always be due to the Birkhoff-von Neumann theorem, since the capacity region is going to be a doubly stochastic matrix, it can, let's see, it can always be represented as a convex combination of permutation matrices. And since our capacity region in general is a substochastic matrix, this term is going to be an upper bound. Okay, here we use the following lemma. If an n by n matrix is doubly substochastic, then there exists a doubly stochastic matrix such that it dominates lambda component wise. So this thing dominates our capacity region component wise, so we can always have this upper bound. Okay, and now with some algebraic manipulation we reach this point. And let's see what we have here. We can always split beta h, and the term inside can be brought outside as a maximum over all the permutation matrices H. And now what do we see? This is achieved with equality because of the max weight. Okay, so the max weight comes in here to achieve this with equality. Okay, so then what do we have? The expected drift is upper bounded by the sum over lambda ij plus n minus 2 epsilon times lambda ij qij. Okay, which so from this we find that the drift is going to be negative provided that the Q's grow sufficiently large, hence the Foster-Lyapunov criterion is satisfied, which means that as long as our arrival rate matrix satisfies this, meaning it is within the capacity region, the Q state, meaning Q of t, is stable. Okay, so this shows that whenever we give an arrival rate within the capacity region, max weight is going to stabilize it, and nothing outside of the capacity region is stabilizable, as we know by the definition of the capacity region. Therefore, max weight is throughput optimal. All right. Now, from the proof of this theorem, okay, clearly Q of t is stable, positive recurrent, so it has a well-defined stationary distribution under max weight. Okay, great, but then the matchings determined by selected by the max weight algorithm also have a well-defined stationary distribution. Let pi h denote the probability that matching m sub m superscript h is selected under the max weight algorithm at steady state. So for any lambda that lies strictly within the capacity region, we can express, we can in fact upper bound lambda by the total rate given by the max weight algorithm, which is going to be a weighted sum over all the matchings m superscript h. Okay, where m superscript h is used pi h of the time. Okay, and the pi h's are just fractions that add to 1. All right, so this means since this is the capacity region, this leads to an alternative definition for the capacity region, which is the convex hull of all matchings. Okay, convex hull of all matchings. If you want, you can go ahead and formally prove this. Now, this is great. Max weight is throughput optimal. However, complexity of finding a maximum weight matching is order n cubed. Why? Because essentially at every time we need to go through every matching, so there are order n squared matchings for every matching we need to compute the weight. Okay, this is may not be practical for some systems, especially 20 years ago. It was not practical at all for high-speed switches, so people really spent a lot of time looking for low complexity switch scheduling algorithms that also work well. And in this, the rest of this chapter, basically we talk about three important ones. There are many low complexity switch scheduling algorithms. This is really a very interesting, very hot research area in the 2000s. So almost, 2 decades ago. This was a very, very active research area, and people came up with very, very nice original ideas. So we'll talk about three things. First of all, we'll talk about maximal matching scheduling, which is really a generic kind of greedy scheduling idea. And then we'll talk about two sort of clever approaches, one of which is pick and compare, the other is load balance switch. These are three ideas that you really should know if you, basically these are benchmarks that you could use in any scheduling situation, whether or not it is about switching. Okay, so now out of these, maximal matching can be implemented with complexity order n log n, and can support any arrival rate matrix which is within half of the capacity region. On the other hand, pick and compare has complexity order only order n, and load balance switching has even lower complexity, constant order 1 complexity, and they are both throughput optimal. Well, of course they have other weaknesses. In general, all of these mechanisms, note that these are all throughput optimal, but we're saying nothing about delay. Okay, so this is a whole research area that if you're interested, you can there's a lot of material to read about. Okay, so let's first talk about maximal matching. A maximal matching is a matching such that if any other edge is added, it ceases to be a matching. So for example, right now, this is a maximal matching because we couldn't add this edge, for example, because there would be a conflict at this node. Can't add this edge, can't add this edge, can't add this edge. So this already is a maximal matching. On the other hand, this is a matching which has the same size, but it is not maximal. Why? Because we could easily add this edge. Okay, so it is easy to see that a maximal matching can be found in a greedy manner. And how would you schedule according to maximum weight, maximal matching? A switch first can remove all the edges with zero weight from the complete bipartite graph, then finds a maximal matching, and then one packet in virtual output Qij is transferred to output port J if that edge exists in the matching. Okay, before how we do this greedily, let's think about an example of the suboptimality of this. Let's see. Consider a 2x2 switch. Okay, assume lambda 1, 2 is 0, so there is no arrival into this queue. Okay, and so this queue is basically gone. and there are these queues. Q12 is always 0. So there are at most 3 edges we need to consider. So basically we can get rid of this edge. All right, so let's consider a specific implementation of the maximal matching scheduling. If Q11 is positive and Q22 is positive, then schedule these 2 edges. On the other hand, similarly, if Q11 is positive or Q22 is positive, schedule the corresponding edge. Okay, and edge 21 is scheduled only when so this edge gets scheduled only when this queue is empty and this queue is empty, so and there's a packet in this queue. All right, so then this implementation gives priority to the virtual output queue. Let's see, virtual output Q11 and virtual output Q22, and serves virtual output Q21 only if the other queues are 0. So in this case, the states of virtual output Q11 and 22 are always, they have no dependence on the state of virtual output Q21, and they're independent of each other. And they are served whenever they're non-empty. So clearly we can form this Markov chain describing Q11. It is the same Markov chain for Q22, of course. And the state is 0. It goes from 0 to 1 provided there's an arrival. And whenever it is 1, it always receives service. So if there is an arrival, it simply stays at 1. If there is no arrival, it drops to 0, etc. Okay, so it is an incredibly easy Markov chain to solve. Of course, you know your birth-death processes. So how do you solve this? Pi 0 times lambda 1 1 over 1 minus lambda 1 1 equals pi 1, right? So by solving this, the local balance equation, okay, it is easy to verify that the stationary distribution of Q11 is 0.5, 0.5. For example, if lambda 1 1 is 0.5. Okay, this means that the probability that both queues are empty by independence of the 2 queues is 0.25. So virtual output Q21 is served only if both Q11 and Q22 are 0, which means that lambda 21 is restricted by 0.25 to guarantee that Q21 doesn't blow up. But on the other hand, the capacity region of the switch is this region, right? In the case lambda 1 1 and lambda 2 are 0.5, according to these equations, lambda 2 1 can be allowed up to 0.5 if the full capacity region of the switch is used. So this example shows that there are arrival patterns and implementations of maximal matchings for which the throughput is below the maximum achievable. Okay, but we can show that the achievable throughput region is not that bad. It is at least it's at least half of the capacity region. How do we do this? Well, first of all, now assume that our arrival rate matrix is within half of the capacitor region, meaning twice 1 plus epsilon of lambda is within the capacitor region. So because of this, there exists an epsilon, by our assumption, there exists an epsilon such that for each j, lambda ij summed up is less than or equal to 1 over 2 plus epsilon. Okay, let me write it down here. This implies that lambda ij summed over I is less than or equal to 1 over 2, 1 plus epsilon for all j. And same thing is true for all I, okay? And we can combine these two inequalities and we can sum them up to get that summation over h, meaning columns of lambda ij plus the summation over k of lambda kj is upper bounded by 1 over 1 plus epsilon. Okay, so that's the first observation, and now we're going to use this now. Now, M of t is a maximal matching, so if Qij is not 0, then either the input port I or the output port j must appear in the matching. So this is the critical part of this proof, because otherwise we could have added edge ij in M of t without destroying the matching property, which contradicts the fact that M of t is a maximal matching. So we know this about the matching. We know this about the matching, and we know this about the arrival process. So we can combine them, right? That, again, we'll make a Lyapunov argument, basically, where, with a different Lyapunov function this time, okay? And then, well, I'll skip the details essentially, but the one-step difference of the Lyapunov function, and you can read this argument in the textbook, can be shown to be upper bounded. No, it's going to be shown to be exactly like this. And now we invoke the two things that we have shown. And you can read it in the textbook. Before you read it, I recommend that you try to do the proof on your own, because you've seen a number of examples by now of using the Lyapunov criterion, the Foster-Lyapunov test. Okay, so I recommend that you try it on your own first. Now, we said this, maximal matching could be implemented greedily, and here's an algorithm, parallel iterative matching. At each time, the switch sets first M of t to 0, initializes it to 0, and if it is not a maximal matching, input port I, if not matched, sends a request message to each unmatched output port j for which Qij is bigger than 0. Okay, each output port j, if not matched, randomly selects one request from the received request and then sends a grant message to the input port that initiated the request. Okay, and the input port I randomly selects a grant message, for example, output port j, and notifies the output port j and sets Mij of t is 1, meaning that that link has now been selected for the matching. Now, so let's see. This is an example of the operation of parallel iterative matching. So here, all the input ports except this, this, and this, all the input ports send requests to output ports for which they have a non-zero Q. Okay. These Qs are 0, so there is no request sent belonging to those. And this output port selected input 1. This output port selected input 2, this output port also selected input 2. Now, this request was granted, and this request was granted. Now, at this point, the matching that we achieved is maximal because there's no more edges that can be added. Okay, so so before that, let's think about the complexity of parallel iterative matching. Each unmatched input sends a request to each unmatched output. Okay, a request is labeled resolved if the request is granted, okay, or if the input port that sends the request is matched, or the output port that receives the request is matched. Okay. Now, because of this, let's show that the expected number of requests resolved at each iteration is at least 75%. How do we do this? Well, let's see. Now, consider requests, consider M requests made to output port J. Okay, and divide these into two classes. Class 1, in class 1 are the requests that are granted by other outputs other than J, and class 2 is the requests that are not granted by other outputs. Okay, suppose there are class K of the requests are class 2. This means M minus K of the requests are in class 1. Okay, now for each class 1 request, the request will be granted for sure because somebody else is going to grant it. Now for each request in class 2, it is selected with probability 1 over K because there are K of these. So these are granted with probability K. Okay. So, because with probability K out of M, with probability K out of M, with probability K out of M, J is going to select a request from class 2. And that request will be granted. Okay. So then the expected number of requests resolved by output J is the following. Well, with probability 1 minus K over M, the output port J selected class 1, so none of the class 2 requests are resolved by J, and the M minus K requests are going to be resolved in total, well, they'll be resolved by other output ports. And with probability K over M, it will select the class 2 requests since basically the output port J will now have been matched. By definition, all the requests will be labeled resolved. So M. requests will be resolved. So if we sum this up, we find m minus k squared over m plus k, which is, you can show that it is equal to k minus m over 2 squared plus 3m squared over 4 divided by m, which is upper bounded by 3m over 4. So the expected number of resolved requests out of m requests is more than, or at least, 3/4 of all the requests. All right, so this is a good point to stop this part of this lecture, and before actually the third part of our treatment of switch scheduling, I ask you to read and think about pick and compare scheduling. I'll see you next time.